Hi, my name is Ta-Wei, and I'm going to talk about fast algorithm via dynamic oracle matrix. And this is joint work with Joakim, Sagnik, and Danupon. So let me first very quickly summarize what we are doing in this paper. So in this paper, we focused on a unified way of solving many problems fast via some efficient reduction to a known and general problem. So one example of this general problem will be maximum flow. So we know that problems like bipartite matching, Gomori-Huchi, edge connectivity, and so on are now run in essentially max flow time, meaning that if we have a near linear time algorithm for maximum flow, then we can also have a near linear time algorithm for all of these problems at the same time. And another common type of this very general problem is matrix intersection. So we know that many problems, including bipartite matching as well, are special cases of matrix intersection. However, we noticed that in the traditional way that people have been looking at matrix intersection, we cannot really say what we did for maximum flow. So that's why in this paper, we try to study matrix intersection in a slightly different setting. And hopefully we can get the same notion of efficient reduction to matrix intersection like we have for maximum flow. And along the way, we got some improvements over known problems. So for instance, this problem K disjoint tree, we have a graph and we want to find if there are K disjoint trees in this graph. So for K equals 1, we just find an arbitrary spanning tree. But for K equals 2, we might have to find a slightly different spanning tree so that the rest of the graph actually contains the second spanning tree. So already for K equals 2, this is getting a little bit non-trivial. So the previously best algorithm was by Gabor and Westerman, and their algorithm for constant K runs in V root E time. And in this paper, we improved this running time slightly to E plus V root V. And this running time was obtained by Quanra independently as well. And I would like to mention that if we just want to get this E plus V root V for constant K, then we are actually aware of multiple ways of achieving this. So for instance, you can use either the techniques in the Karger paper or the techniques in this newer paper alongside the Gabor and Westerman's algorithm to achieve this result. But doing so will have a worse dependence on K, and it will also be less general than the algorithm that we described in this paper. So our algorithm actually works for a larger class of problems, not just this K-disjoint tree one. Okay, so now let me define what a matroid is. So the matroid N is defined over a ground set U of n elements, and it carries a certain notion of independence I over the subset of ground sets. So we have a family I of independent sets, which will have to satisfy a certain property, but I'll ignore that for the purpose of this talk. And we'll be using the following two definitions. So the rank of a set S is defined as the size of the maximum independent subset of S. And the basis of a matroid or a basis of set is simply a maximal or maximum independent set. So for instance, in colorful matroid, we have a bunch of elements. Each of the elements has a color on it. And we say that a set is independent if it does not contain elements with the same color. So for example, this set is independent. This set is independent as well. However, this set contains two green elements, so it is not independent. But we can still compute the rank of this set, which will be equal to 4, and this corresponds to the number of distinct colors in this set. And another example is graphic matrix. So given an undirected graph, we can define the graphic matrix over the edges of this graph. And now we say that an edge set is independent if it does not contain a cycle. Now, the rank of the edge set would be something corresponding to the number of connected components that this edge set induces. The matrix optimization problems that we're studying in this paper are the following two. So the first one is matrix intersection. We're given two matrices M1 and N2. They are over the same ground set U, but they will have different notion of independence I1 and I2. And our goal is to find the maximum set S, which is independent in both matrices. So this will, for example, model the bipartite matching problem. So if we define the matrix to be over the edges of this graph, then in the first matrix, we can say that an edge set is independent if for each vertex on the left, it is incident to at most one edge in this subset. And this can be modeled by the colorful matrix of this coloring. And for the second matrix, we can do the same thing for vertices on the right. Now we can see that any edge set that is independent in both matrices will form a matching in this graph. So finding the maximum intersection of the two colorful matroids correspond to solving the bipartite matching problem. And the other problem is matroid union. So now the input has K matroids, and these K matroids may have different ground sets, and they may also have different notion independence. And our goal is to compute the maximum set S, which can be written as the union from S1 to Sk, where Si is an independent set in the ith matroid. And a particular special case that is often very relevant is this K-fold matroid union problem. So we now assume that all the K input matrices are the same, and therefore the output will correspond to finding the maximum set S, which can be partitioned into K independent sets. So this will very naturally model the K resource spanning tree problem. If we just set M to be the graphic matroid, then finding K spanning trees directly reduces to solving the K-fold matroid union problem on this graphic matroid. And there are many other problems which can be modeled by matroid intersection and matroid union. Another example will be colorful spanning trees. So now we have a graph, edges have color, and we want to find a spanning tree in which every edge has a distinct color. And matroid intersection is also a special case of model function minimization, which is another important optimization problem in the literature on its own. And notation-wise, throughout this talk, I'll be using N to denote the number of elements, and R will be the rank of the input matrix. So for graph applications, you can think of N to be the number of edges and R to be the number of vertices. And one thing that I didn't mention before is that how do algorithms solving this general matrix intersection or matrix union problem actually access the matrix? And this is a problem because in general, an explicit description of a matrix will be exponentially larger than the number of elements in it. So we cannot hope to just feed the matrix completely as input to the algorithm. So what is usually done in the literature is that we give algorithm oracle access to the matrix. So two common types of oracle are independence oracle, which if you give it a set S, it would determine if S is independent or not. And in the other type is this rank oracle, which will simply compute the rank of S. So now in the traditional model of matrix intersection, so the word traditional is used to distinguish between the models that people have been studying before and the new model that will be introduced later. So in this traditional model, our goal is to minimize the number of queries, either independence query or rank queries, in order to solve matrix intersection or matrix union. But this actually brings our attention to this interesting question, which is that on one hand, we now know that matrix intersection can be solved quite efficiently. So we have this unruled out rank query algorithm for general matrix intersection by Chakrabarty, Li, Xu, and Wang in 2019. On the other hand, for many of these specific matrix problem instances, the state-of-the-art results are actually this E root V algorithm, except for bipartite matching. So for bipartite matching, this is the best combinatorial algorithm for it. So these algorithms were developed in the 80s and 90s, and they are sort of specialized in the sense that the authors has to specialize the high-level matrix intersection framework to work for each individual matrix and get this efficient running time. But as a big goal of studying matrix intersection is that we try to get a unified way of solving many problems at the same time. So we ask, does efficient matrix algorithm in this traditional model actually imply efficient algorithm for problems on the right? And in particular, now that we know we have this unruled out rank query algorithm, can we automatically recover the running time of this E root V algorithm for free via a black box reduction? And the answer is unfortunately no. And this is because in order to run general matrix intersection algorithm, you have to implement the rank oracles for it. But to compute the rank of a set, regardless of what matrix you're looking at, you need at least omega s time just to specify the set S and feed it to the oracle. So hypothetically, even we can get optimal and linear rank query algorithm, then using this reduction, we can at best get some quadratic algorithm for problems like bipartite matching, which is apparently too slow. So as I mentioned at the very beginning, the central question that our paper is studying is whether we can get the notion of efficient reduction to general matrix intersection algorithm, and therefore a unified way of obtaining algorithms. So not just an algorithm, but efficient algorithm for specific matrix problem instances at the same time. So that's why we introduced this new model that we call a dynamic oracle model. So the motivation of this model is very simple. So we know it is certainly hard to compute rank of S from scratch because it takes linear time just to specify the set. However, if we have already computed rank of S and we want to add or remove some elements to it, then maintaining the rank of this new set from what we already have might be potentially much easier. So for instance, for colorful matrix, this corresponds to doing some counting, and this can be done in constant time. And for graphic matrix, we can also use some dynamic connectivity data structure to maintain the number of connected components, and this also only takes polylog time per update. So now, in addition to issuing few queries, we also want these few queries to be close from each other so that we can maintain the rank or the independence of a new set from the rank or the independence of a previous set. So formally speaking, we can define the dynamic oracle as follows. So at the very beginning, we have a set Q0, which is empty. And now in the case query, we actually restrict our algorithm to only ask set Qk, which comes from a previous set Qi, and we're allowed to add or remove one element to it. And we call this single insertion or deletion a dynamic query. So now instead of minimizing the number of rank queries or independence queries, we actually want to minimize the number of dynamic rank queries or dynamic independence queries that an algorithm needs to solve matrix intersection or matrix union. Okay, so now we can see that suppose we have this unruled out dynamic rank query algorithm for matrix intersection. Then throughout the execution of this algorithm, we can implement each of the dynamic rank queries that the algorithm uses with appropriate data structure. And in fact, for problems that are listed below, there were actually very efficient data structures, so polylog update time data structure for their dynamic oracles that were already developed in the literature. So this only incurs a polylog update time over our running time above, as opposed to the linear overhead that a traditional algorithm must suffer. And also you can see that if at one day we are able to improve this unruled out running time to near linear, then this will automatically give us an improved algorithm for all of these problems below using the same reduction. And even for some harder matrix, we might not be able to get the efficient data structure with polylog update time. Hopefully, we can still get a dynamic algorithm that is slightly better than just recomputing everything from scratch every time. And therefore, using this framework, we can still be better than running the traditional rank query algorithm and using static algorithm as implementation of their rank oracles. Okay, so now given the introduction of this new notion of dynamic oracle, let me now mention the technical results that we have in this paper. So as I hinted earlier, we showed that matrix intersection can be solved in unruled out running time and dynamic rank queries. So this is stronger than the Chakraborty-Lisi for sigma Wang's algorithm in the sense that the query set that the algorithm use are close from each other and therefore can be maintained efficiently. And as a byproduct, we also have a dynamic independence query algorithm that matches the current state-of-the-art traditional independence query algorithm. And for matrix union, since there's a standard reduction from matrix union to matrix intersection, theorem 1 already gave us a running time of n-ruled r. But in this case, we slightly improved the running time to be n plus r-ruled r, and this also works in the dynamic rank queries model. And this will, for example, imply the v root b k-digital explanatory algorithm that I mentioned at the very beginning. And finally, we have some results from the lower bound side. We show that to solve matrix intersection, you need at least n log n queries, and these queries can either be the new dynamic rank queries that we introduced or the traditional independence query that people have been studying. And actually, our second lower bound, the traditional independence query lower bound, answered an open question that was asked in the past. So people were wondering whether we can prove some superlinear lower bound for matrix intersection. And our results show that indeed you need at least n log n queries. And this improves the 1.5n lower bound by Harvey. And as direct application to our dynamic rank oracle model, algorithm for matrix intersection, and using data structures that people have already developed in the literature, we are able to get all the running time shown here at the same time. So for problem at the top, these problems generally use some primitives similar to the k-digital explanatory problem. So we are able to get a running time of e plus v root v. And for problem at the bottom, we are able to match most of the state-of-the-art results that were specialized to work for each individual matrix combination. And we're able to obtain this running time in a unified way. But one caveat here to notice that is that for some problems at bipartite matching, we now know that we can reduce it to maximum flow and solve it very efficiently using the new max flow algorithm. And our algorithms are not quite there yet. We can only match the best combinatorial algorithm for bipartite matching. This is the Hopcroft-Carr algorithm. However, the main advantage or the main goal of this framework is that hopefully it's now easier to design new and efficient algorithm for new problems. So for instance, in this paper, we made up this problem called maximum forest with deadlines that we're seeing is a reasonable enough optimization problem. And using our major intersection algorithm, we're able to automatically get an efficient running time of E root V for this problem directly. And if in the future, we are able to improve the running time of our major intersection algorithm in a dynamic oracle model, then this improvement will also be available for this maximum forest with deadline problems and others as well. Okay, so now let me talk a bit about the techniques that we use in this paper. So for major intersection, we follow the Chakrabarty-Lee-Seafold signal-Wang's blocking flow kind of framework. And like most of the major intersection algorithm, we work by repeatedly finding augmenting paths and enlarge our current solution. So say we already have a common intersection capital S, then we can define a so-called exchange graph with respect to S. And this graph will be a bipartite graph with between elements outside of S and elements in S. And we use edges in this graph to model some local exchange relationship. So if we can exchange two elements while still maintaining the independence in one matrix, then we add an edge between these two vertices in the exchange graph. So now, if there's an ST path in this exchange graph, then we can notice that there are more elements on this path that are outside of S than elements inside of S. So if we augment along this path in some sense, we'll be able to get a larger solution and then we make progress. So now the problem is that this graph in general can be very dense, so it can contain a quadratic number of edges, so we have to explore it in a somehow sublinear fashion. So what Chakrabarty-Lee-Seafold signal-Wang's algorithm does is that they use some sort of binary search to very quickly locate what the next unexplored neighbor of the current vertex is. And therefore, to adopt their strategy to our dynamic oracle model, we have to somehow make sure that the query sets are close from each other. So that's why we built this binary search tree kind of data structure, which essentially contains every query set that we will need in order to perform a series of binary search to find a single augmenting path. And after we find a single augmenting path, we'll need to update the tree entirely, but that's too expensive to do so. So we additionally employ some lazy update kind of algorithm to batch several updates together and only rebuild the tree entirely every few iterations. And finally, we have to apply some structural lemmas that are known to the exchange graph to further reduce the number of updates that we need to make our final algorithm efficient. And for matrix union, since the focus is on improving the n-rudar running time to n plus r-rudar, you can think of n to be much larger than r in this case. And what we notice is that if we just solve matrix union using matrix intersection algorithm, then the first layer of the exchange graph will always be much larger than the rest of the graph. So the first layer will contain roughly n elements, while the rest of the graph contains only r elements. And also, to find a single augmenting path, it suffices to only consider a basis of the first matrix instead of everything in it. So now the problem that we have to solve is that once we find an augmenting path, some elements might be removed from the first layer and we have to find a new basis. That's why we designed this decremental data structure, which maintains the basis in a set efficiently in the dynamic rank query model. And we achieve this via some square root decomposition as sparsifying trick, which is inspired by this dynamic minima spanning tree algorithm in the past. And we generalize this to work for an arbitrary matrix. And for lower bounds, we get our lower bounds by studying the communication complexity for matrix intersection. So we prove that if we have a certain lower bound for the communication complexity, then we'll get the same lower bound for query complexity of either a dynamic rank query or traditional independence query. And the reason why this reduction hold is that a single dynamic rank query or a single traditional independence query actually only reveals a constant bit of information to us. So say for a single dynamic rank query, we know that the rank of the new set can only be the rank of the old set +1, +0, or -1. So there are only 3 possibilities. And for the communication complexity of Matroid intersection, we use this unlog and lower bound for the communication complexity of ST connectivity. So determine whether 2 vertices are connected in a graph or not. And we noticed that Matroid intersection in the communication setting is harder than ST connectivity. And this is because even just to verify whether a given set is the largest intersection, we have to determine whether there's an ST path in the exchange graph. And somehow by carefully choosing what matrix we use, we can control how the exchange graph looks like to be essentially equivalent to the input of the ST connectivity problem and complete the reduction between these 2 problems. Okay, so finally, let me mention some interesting future directions. So the first one is maybe we can look more closely into this colorful spanning tree problem and trying to get fast algorithm for it. And this problem may on its own seems like a toy problem, but it is actually interesting in some sense. So it's generalized the bipartite matching problem. But for bipartite matching, we know that we can solve it very efficiently using the new max flow algorithm. But these new algorithms all use some sort of continuous optimization techniques, and in particular, the interior methods. And currently, we do not know how to use this framework for problems whose linear program has exponentially many constraints. So colorful spanning tree will be one such example. We have to somehow encode the fact that the solution forms a forest or a spanning tree. So that's why hopefully by trying to get faster algorithm for this problem, we can either have a new way of using interior methods for these kind of problems, or a faster combinatorial algorithm for it, which will also work for bipartite matching. And another problem that is very interesting on its own is this k-disjoint spanning tree problem. And this is because a closely related problem of finding k-disjoint arborescence or directed spanning tree in a directed graph can actually be solved very efficiently in near linear time for constant k. However, in the undirected case, even when k equals 2, we don't know anything better than the E plus B root V algorithm that we described in this paper. So it is very interesting to see whether the directed version is actually harder than the undirected version. Oh no, the directed version is actually simpler than the undirected version. And conceptually, we can also try to introduce the notion of dynamic oracles to other problems as well. So problems like some modular function minimization or maximization are studied in the setting of oracle complexity. So maybe we can see what applications we'll get if we have a notion of dynamic oracles there as well. And finally, I would like to mention that improving our lower bounds is also very important. And in particular, in this paper, we show an n-log and lower bound for dynamic rank queries or traditional independence query. And in some sense, a common ancestor of these 2 types of query is the traditional rank query. And in fact, if we can improve our lower bounds to work for the traditional rank query model, then this will actually imply an n-log and lower bound for submodular function minimization, which works for weakly polynomial time algorithm. So right now we have an n-log and submodular function minimization lower bound, but this lower bound only works in the strongly polynomial regime. So that would be one implication if we can slightly improve our lower bounds. And of course, if we can even improve our lower bounds to be some truly super linear bound. So if we can get polynomial improvement over our lower bounds, then that would be even more exciting to see. Okay, so this concludes my talk. You can find our paper on arXiv here, and thank you very much for listening.